Hello, this is Miss Abney. In this video, we're going to cover example 2 from topic 1, lesson 1-5. And in this one, this one's a little bit different from example 1. Looking at this, we want to solve an inequality. So basically, for lack of a better term, we're going to have alligators in our solutions here. And since we're looking at inequalities, we're going to look at groupings of areas where our solution actually does relate. So just like before, in example 1, we're going to break this out into two expressions. All right. So we're going to have f of x equal to x squared minus 4, and g of x is equal to 0. And when I go into Desmos to graph these, and again, we could graph these by hand by making the t-table. Actually, so again, you could make the t-table, or the h-table in this case. And then you could have your x and your f of x, and then your g of x. And I would pick numbers around 0, because g of x, no matter what, is going to be 0. And then because we're talking about transformations and translations in topic 2, we actually have a translation down 4. This is a vertical. That's because the parent function was x squared. And again, if I were to box anything that is contained in the square, from here to the square, this is happening outside, so it's vertical. Move down 4, so this should not make a difference. So this is going to be -2. And what I'm saying in my head is, do I have to actually move my parabola from the origin? Because this is a parent function. Do I have to move it this way or this way? And because we're moving it down 4, moving it down here, the vertex will still be at 0. So that's what I'm thinking in my head while I was trying to decide my values. And then again, we'll plug this in. -2 squared is 4. 4 minus 4 is 0. -1 squared is 1. 1 minus 4 is -3. This should be -4, -3, and 0. Yeah. And so what we'd be looking at graphically by hand, and I'm just doing this quick one by hand. We're going to go over to Desmos because it's a little bit easier to read. But I just kind of want you guys to see. And then here at 2, we're at 0, 0. And then this is at 3 and 3. Not drawn to scale. My beautiful wobbly parabola. Ooh, that is not. Yeah, this is beautiful. I hope your guys' take shape a little bit better than mine. All right. And then the second one, the g of x, is going to be right here on the when x equals 0, or sorry, when y equals 0 for all x. That's a little too thick. When y equals 0 for all x values. And what we're looking for is when this function, actually we could probably work off the graph I have. We're looking for when this function is greater than this function. And so looking at that, we are going to see that the values, let's go with the highlighter. We can see that the values from here to this point, and here on, sorry, sound effects, we can see that is when the f of x is greater than the g of x. So the way that we would state this is I would say x squared minus 4. X squared minus 4 is greater than 0 over the interval. And I want to make sure I got this written down correctly. Over the intervals. And again, it's the intervals because we're looking at over here from negative infinity to this value, which I believe I should be marking my graphs. That's a good practice to mark the graphs. From negative infinity to negative 2. And then here's where they cross, and this is not equal to. If this was equal to, then we would include negative 2 in the value. But because they're not equal to, we don't include it. So we use the parentheses as opposed to the brackets. And this is from 2 to infinity. Okay, so along those intervals. So I'm going to write on the intervals, negative infinity, negative infinity. Oh, I don't know what kind of infinity that is. Negative infinity, comma, negative 2, and 2, comma, infinity. All right. Or you could also say x squared minus 4 is greater than 0 for x less than negative 2 and x greater than 2. And that's what they do here. So they're talking about looking for points on the graph where the function is positive because that x or y equals 0 is the x-axis. We have intercepts or zeros at 2 and negative 2. And so we have this statement is true for x less than negative 2 and x greater than 2. All right, so the second part, we have a motorcyclist. And this one says, how can you use the graph to solve an inequality? A motorcyclist is 40 miles ahead of a car. The motorcycle travels at an average rate of change of 40 miles per hour. So remember, average rate of change is that, or the average rate is that change of your rise over change of your, or rise over run. The car travels at a rate of 60 miles per hour. When will the car be ahead of the motorcycle? So this is going to make us think a little bit. I love that graphic. Kind of wish they had it in a video. That'd be pretty cool to see the car and the motorcycle in this race. Make this a little bit smaller so I could fit onto the page. Here we go. I'm trying to think of how I'm going to start tackling this because I was thinking I should just start with the graph. And let's see if starting with the graph helps me out here. So a motorcycle is 40 miles ahead of a car. So an average rate of change, which means if this is linear, my slope is going to be 40. And so here's the car. And the motorcycle is 40. So I'm going to use this as distance. And this is time. So the motorcycle is 40 miles ahead. It's growing at a rate of 40 miles per hour. Let me use green here. And then this is just going to be a rough sketch. So my rise over run is so not drawn to scale. Let me try to draw it to scale a little bit better. There you go. And let's make 40 down here. Because we're talking about cars, they could get pretty far pretty quickly. So this is 1, 2, 3, and this is in hours. And I could tell this is hours because my rate is 40 miles per hour. Then this point would be 80. This point would be 120. This point would be, did I do that? 160, I believe. All right. So this is him going at 40 miles per hour. And what I did in my head there is I know that we started at 40. And after 1 hour, he went another 40 miles. So that's the 80, and then the 120, and then the 160. And that's what I did with each of these. The car travels at a rate of 60 miles per hour. So after 1 hour, the car is about here at 60. 2 hours. I don't know why I put that. The car is here at 120. And 3 hours, the car is at 180. So a little bit higher up. Oh, that's not even a line. Let me erase this and make this more linear. So essentially the car would have something more like that. So if I were to make the motorcycle, I start the motorcycle, it's linear, and we intersect the y-axis at 40 for the motorcycle. Well, the car, our y-intercept is 0, so that's going to be plus 0 here, and our average rate of change is 60, so that's 60x. Now I want to know where they intersect. I could see here, I'm going to guess that they intersect at 120. Because that appears to be when they both go through. And that happens to be at 2 hours. So when time, I'm going to say t equals 2 hours. The motorcycle. Oh, I should actually write this out other than just say it. It's good practice to write things out. So the motorcycle. It's not the motorcycle approaching the car. The car will be ahead. Ahead, D. When T, and we're talking about all the time that the car is ahead. So the car is going to be ahead for any number greater than that 2 hours. So all of this here, and these are lines, so this will continue to grow at 40 miles per hour, and this will continue to grow at 60 miles per hour. So from this point on, from h equals 2 on, the car will be further than the motorcycle. I should put of the motorcycle. And the whole reason I use t instead of, I know I used x up here. The whole reason you should use t instead of x is because we're talking about time. And so t is actually a very good variable to use for time. You could use x. That's a weird t. But there you have it. And if you want to double check if your graphs are a little bit off, you could come up with the equation. Remember, when we're talking about rate of change or miles per hour, we're looking at rise over run. And if this is a line, we're looking at slope. So again, miles per hour, this is an average rate of change. And we've talked about this, the average rate of change being your y2 minus y1 over x2 minus x1. So there's the motorcycle problem. And now you have a try it. So use the graph to solve the inequality. Here you're looking for when it's also equal to 0. So you got to include that in here. So you have your parabola here. This one you could again make a t-table, but they provide you the graph, so I just jumped straight into the graph. Your one function is going to be the left side, the other function is the right. Even though that's 0, that still can be a function. It's just a constant. And you could plug it in here. And not 0, 6. I believe you have to say y equals though. And it'll draw you the line. Check your answers for that one once you've shown me the interval. And then again, you're doing an interval here for when the left is greater than the right. So there's example 2. If you have any questions, any comments, please leave them in Classroom or email me or contact me, and we will be seeing you.